Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on Building Energy Systems and Auditing. In the module number 4, we are discussing Energy Conservation Building Code ECBC. In the lecture number 19, the daylight concept will be discussed. So, in this particular lecture, the daylight factor, the sky component, the external reflected component and the internal reflected component will be discussed, and we will also see how a daylight factor can be calculated. So, as we all know, the sun is the source of light, and this daylight is being tremendously used in our building since ages, and this particular the sunlight has a potential value from all respect. It has a value on the sense of it gives very pleasant atmosphere, indoor atmosphere, it is also very healthy. So, through windows and some the fenestrations in the building, we allow daylight penetrations also. So, the amount of daylight will be penetrated into a building, it is actually going to save a lot of amount of artificial lighting, of course, during the daytime. So, if you see the daylight, the advantages of the daylight, it is natural. So, that is one of the biggest advantage. You do not require any kind of the energy. It actually going to minimize the artificial lighting cost or lighting load during the daytime, but it is total artificial lighting load or cost is almost about 15 to 40% of the building electrical cost, electricity cost. It also lowered the HVAC load because of the if there is less amount of appliances in the daytime in service. So, the equipment load is also going to be less. So, it is hygienic, it disinfect a lot of bacteria and virus during the in the indoor atmosphere. So, it is always going to be good, and it has a very good impact in the mental well-being and also the productivity and overall development of. So, there are different parameters which are actually going to have a vital role in the daylight or daylight calculations or in a daylight in a particular indoor atmosphere or indoor environment. So, it depends upon the orientation of the building, it depends upon the time of the day when I am going to actually the measure or I want to have the daylight. Its building shape and orientation go hand by hand, because sometimes a proper orientation you may have placed a building, but the shape of the wall or that may not invite that much amount of daylight, or shape of the wall I mean to say that the slope of the wall, maybe it is a very inclined kind of a wall, or maybe some other obstructions are there, maybe it is a mutually shading kind of a scenario. In that particular orientation, it may not give that much amount of daylight, or in other words, sometimes it such a way placed that it invites daylight inside the interior. Size and locations of the opening, we will discuss that one. Of course, this is one of the very prime factor for daylight consideration. Location of the room, again it is depend upon the room location in the horizontal, the orientation of the building, or maybe sometimes when it is if you vertically see after certain level you do not have any kind of obstructions, or so the trees, the other smaller buildings in your periphery. So, that will of course going to give you much more amount of the penetration of the daylight. The interior color, exterior obstructions, these are also going to help us for the daylight penetrations or so, or maybe the stabilize the daylight inside the building because of the multiple reflection. So, next let us discuss about the daylight factor, which is very important to know and very important parameter to understand the how much daylight can a particular point or particular work in a particular working plane, a certain distance from the window or maybe certain distance from the corner, a particular position, say may say can get the amount of the light as a daylight or so. It is a simple factor, it is simple ratio E I by E naught or E O. So, the E I is the indoor illuminance at my point of interest, and the E O is the outdoor the illuminance in the obstructed sky hemisphere, and that is multiplied by 100 gives you a percentage kind of a scenario. So, these are the some of the sky conditions, and depending upon the sky condition the illuminance are measured, and that was given in lux, that is the unit of the illuminance we have seen in the second chapter, second module. So, the brightest sky has a very huge amount of the illuminance, and that is received by all the typical surfaces of the building, and then from it is penetrated, and it will be the daylight will penetrate, and then it will be some part of it, not definitely the whole, some part of it, because depending upon the aperture size and all these things will be going to illuminate the interior. So, typically if I just go down, so the overcast sky, clear day at sunrise and sunset, it is little less, almost about 300 to 400 lux. Extreme overcast sky with the clouds in time of monsoon and all, it is further go down. So, normally for our calculation we always do not take the brightest scenario, always will not going to take the overcast and cloud scenario. So, we assume almost about 6,000 to 800 lux as our calculation purpose for the outdoor atmospheric the unobstructed sky hemisphere illuminance as EO. So, that is one of the very important things. So, we should see that. So, this is one of the very important the point that I want to mention. Now, a daylight of course, this whatever we are discussing is a part of your climatology, and probably you have learned that in the second year of architecture. So, but it required to know, because in the next lecture what we will going to define, it is based on this particular daylight factor or so. As ECBC also stated that some of the recommendations. So, we need to understand this particular daylight factor first in a little bit of deep into detail. So, first of the contribution in this daylight are specifically classified into three major category. One is the sky component. Sky component is the component which actually directly come from the sky, the hemispheric sky or that particular illuminance. Because of the solar radiation, the whole sky is now like the source of light, and from there it comes to through the windows or so. So, from the directly it is from the sky. So, this red lines, this one is the sky component, it is direct comes from the sky, and sky is the source. The second one is the externally reflected component. There will be some kind of obstructions, or there some kind of buildings, or maybe some surfaces. So, it will not come directly through the window, but it will come via some kind of the reflection on the external surfaces, ERC, the external reflected component, which I have shown in the purple color. So, it is also may come. The third one is the internally reflected component. Internally reflected component is the component which is green one, the IRC, which actually come to the working plane because of by virtue of the reflection from the interior ceiling or maybe the interior wall or so. So, this particular internal reflected component will be high if I have a light color the interior surfaces. So, the amount of reflection will be much more, the dark color surfaces will going to absorb more amount of daylight. So, the reflective the proportion of the reflection will not so much. So, it will be less. So, that way internal surfaces, the color of the internal surfaces and all those, sometimes it is the external little bit of paving very near to the windows or so, and through that reflections can go to can strike your ceiling through the window and then come to the working plane. So, light color interior are the one of the solutions or one of the way that we can improve the internal reflection coefficient or so, component. Now, we will see that how we can compute this particular daylight factor. So, we will I will go back a little bit, we will actually see this particular fundamental equations is actually based on the sky component. Sky component is one of the component out of these three component of the daylight factor, the sky component is the major one. Because it is the actual illuminated source of light, the daylight, from where directly the daylight is actually penetrating through the windows or fenestration and actually impacting in my working plane or fall incidence on upon working plane, and because of that the working plane surface is illuminated. Other two are definitely going to reinforce that, the first one, but it is not the primary one. It is going to reinforce the a bit, or maybe it is essentially it is going to give you some amount of enhancement, but not the prime one. So, this particular calculation of the daylight factor is this particular equations or this particular the formula is based on the sky component point of view, where the df is categorically equated with some of the parameters which we just now we have discussed. The first one AW is the particular opening of the window, the area of the opening of the window. So, for the daylight calculation. So, I want to calculate indoor in some of my point of interest, and that point of interest has a location, that means it has a particular coordinate with respect to the length and the width of the room, and also of course, with the height of the room. So, there is a 3-dimensional point or on a space, and from that point of my interest point of view, the window, the size of the window which I am going to the daylight comes through that particular window, and I want to find out what is the proportion of the daylight factor comes from the window. If there are several windows, not 1, 2, 3 or 4, so for each and every window I have to calculate that, and with respect to the window locations my coordinate may change, that internal point of interest coordinate may change. So, the AW is the area of the window, then small t is the visible light transmissions of the opening of the window. Now, window the character of the window, it is a translucent kind of a material like a glass or something, but it has a visible light transmission capacity. So, it may not, it may be little dark in color. So, it is going to will not 100% it will not going to pass, maybe only 70% or maybe only the 60% will going to pass, or a very clear kind of a glass. So, it may actually the 95% of the visible light may pass or something like that. So, that also required to be know as a the part of the visible light transmission of the opening. Theta is the angle, the visible sky angle from the midpoint of the window. So, it is a you have to find out that particular angle by virtue of some trigonometric relations, a very simple trigonometric relationship. We will see that in the next slide. The AS is the total surface area of the room. This is important because when the daylight will come, it actually going to spread over, actually spread over, and that particular spreading over, there may be some kind of the another internal reflections and going to again reinforce that particular daylight in at that particular point, but initially it will going to spread over, and then because of the internal reflections and all, it will going to accumulate. That R is the average surface reflectance of the room. So, that is what we are talking, that if it is a light in color, light color, it is higher or so. So, 0 to 2% daylight factor is inadequate, and it may not a good condition, and we may require electric light to supplement that daylight factor. 2 to 5 is adequate light, but sometimes it may require electric lighting, because sometimes it is dark because of the cloudy day or whatever. So, that is why it is the middle point 2% to 5%. If it is more than 5%, so DF is more than 5% good, then it may well lit, but sometimes it may give some kind of a glare, or some point of the glossy surfaces may give some kind of a glare. So, this is the visible light transmission, which is this T, small t we talked about. The spectrum which 380 to 720 nanometer, we have already discussed that one, the sunlight spectrum which actually transmit the visible component of the light. So, that is going to be how much that is penetrating, how much percentage of that is penetrating. So, if it is a very light tint color tint glass or so, it is almost 80 to 100%. So, 90% maybe, and the last one you see very dark tinted glass, very dark tinted glass, sometimes we use that glass in our the four-wheeler or so. So, those glasses can have 3 to 18% of the transmissions. So, this is the some standard, and the light reflectance values, that how much the value, how much percentage of the light is going to reflect because of the different type of color, interior color, and that will going to reinforce the daylight factor or in that particular location that I am going to find out. So, these are the things. So, it is, if it is a black, the last line, the black, it is almost 1 to 4% is the reflectance. So, almost about 96% to 99% is going to be absorbed by the surface, whereas if you go to the top, the white color surface, interior surface will going to reflect almost about 90 to 70%, 70 to 90% of the light, and almost about the 30 to 10% is going to absorb by some other means. So, the ivory cream, the light yellow. So, those are the some color list, and if you see as and when you are going little downward, the things are, the colors are little bit darker in shade, and your percentage value is decreasing gradually. So, the one thing that we have to discuss, that theta, that is the visible sky angle. So, it has to be measured from the midpoint of the window. Even your window is not obstructed, but it has to be taken from the midpoint of the window to get the clear sky component of your sky or so. So, if there is some kind of obstruction that it is going through, this particular diagram is not very correct. So, this dotted line should pass through this. So, and this will be the theta then. So, because of the obstruction, the theta value is decreasing. So, theta comes in the here. So, as theta decreases, definitely your DF is going to be decrease. If the T is increased, that is the transmissibility, the visible transmissions and all light transmission, it will going to increase. If your area of the window is increased, definitely your daylight factor will going to increase, that is obvious. If your R is going to increase, 1 minus R will going to decrease, or 1 minus R square will going to decrease, and then it will be definitely DF going to increase. And if the area of the total surface area of the room, that is going to if you that will increase, definitely it will going to decrease also. So, here we have done that one, a small problem. So, we are finding out, this is the window, 2 meter is the the area of the length of the window, and in sections I have mentioned that this is the height of the window is 1.5 meter. So, the room area is 6 meter. You see this is the 4 plus 1 2 plus 1 plus 1 is 4 meter by 6 meter. So, this is the room area. Room height is, I have assumed that as a 3.5 meter. Of course, in this particular the section drawing you can see this is 1 meter plus 1 meter, 2 meter and 1.5 meter. So, 3.5 meter is the room height. Window dimension is 2 by 1.5, that is also mentioned or shown in that. There is a door also, the door dimension, this is the door, this is the door, this is the door, and the door dimension is 1 meter by 2 meter. So, my point of interest is A and B, which is 2 meter and 4 meter respectively away from the center point of the window, and that is also 1 meter above the floor. So, above the floor is, you can see it is from the section drawing, and the horizontal position you can see from the plan drawing. So, this point A and point B are having some static point, some kind of a coordinate 2 meter and 4 meter from the window and 1 meter above from the floor, and I am going to calculate what happened if this is particular, this window and all these things are there, and what will be the daylight factor. So, here first I have found out the theta. So, I know this will be the angle theta. So, I think I have measured the angle theta. So, this is 2 meter for A, 2 meter and this 0.75, 0.75. So, I have used some kind of the trigonometric relationship, and I found that the theta A is equal to 16 degree. Similarly, I have calculated the theta B, which is now 4 meter. So, see this is instead of the 2 meter, now this has to be in 4 meter. So, geometrically it is from the triangle is extended to the B. So, now it is 4 meter is the best instead of that, and tan will give me give me the theta. So, it is 10 degree. So, I use that one. So, I have measured the surface area, I have measured the window area is 3 meter square, because it is 2 meter by 1.5 meter or so. Visible is light transmission coefficient 0.8, R I have taken 0.5, and this is the surface area. So, now just have to put and this is the theta values, and I have to put the right place. So, I got 8% 0.8% is the daylight factor on point A, which is the closer, and 0.5% is the point B. Definitely it will be lesser because it is not so close to the window, but these two values are not very good values, as we see it should be around 2 to 5% to have a good value. So, anyway this is our calculations also. So, that is why we got some values like this, and let us go to the next one. So, next one what I did is that I increased the window width by 3 meter. Instead it was 2 meter if you remember, now I have increased that by 3 meter, only that is the only change. If that is the change, there are little bit of changes will be there. The area of the window now become 4.5 meter, this T values and the R value remain unchanged. The surface area of the particular room, and please remember the surface area is a wall surface area, and the of the room is now going to be little less. So, it is because the window is more. So, 63 point, though there is a change, 63.5 meter square is the area of the surface. The theta A and theta B remain same, because your height of the window remains same 2 meter and 4 meter, that is I am sorry, that is your 1.5 meter remains same. So, there is no change in that. So, that is not going to be changed. So, 16 degree and 10 degree. So, I recalculated with the new values. So, now it is to 1.2 and 0.75, it is improving because I have increased the window size from 2 meter to 3 meter width, and the window area is also increased. So, that definitely the daylight factor is improving, and it is from 1.2% now, which was around 0.8% or so in A. Now, what I did is that I again come back to the first the case, the width of the window is 2 meter, but the height of the window instead of the 1.5 meter, I increase it to the 2 meter. So, the height of the window is increased to 2 meter. So, again there are some changes, the changes in the total window area, there is a change in the total surface area, but these two values remain unchanged, but here you see the tan values also has to be changed. So, all the changes, the value where there is a change I have mentioned in the red in color. So, 2 1 2 1 those are in red. So, here the size or the height of the window is 2 meter, not 1.5 meter. So, once I have to take 2 and second part of the tan inverse I have to take half of that 2 is 1. So, now your aperture angle which was 16 degree and some other 10 degree. So, now it has become 18 degree and 12.5 degree, aperture is increased. So, the theta angle between that the midpoint of the window and the top portion of the window, that particular aperture has been increased because of the increment of the height, and I have to again put the corresponding value of the in this equation. So, the 4 is the AS is the 4 and the 64 is the 4 is the area of the window and 64 is the surface area, and all other things 18 and 12.5 is the angle of the aperture angle. I got 1.2% of DF for point A and point B is 0.83%. So, the point B has improved, point B has improved from point, I think is this, yes, this was 0.75 and from 0.75 to it improved to 0.83 because of the height change in the height, the improvement or the increase in the height, the B was in the back. So, the more daylight comes to the back side, but in the front side it remains same 0.12. So, I have a chart. This see the when the base case, what we have kept in the base case, the width is 2 meter and the height is 1.5 meter. The window area is 3 meter square and DF for A is 8.8% and DF for B is 0.5%. I am actually using 6000 lux as a LO. So, from that point of view I calculated the EA and EB. I think this is the my calculation the equations. So, EI I have calculated, I put this value as a 6000, this is the average value, and DF is your 0.8% or whatever I have 0.8 I have to actually give because it is by 100. So, 48 lakhs and 30 lakhs, 72 and 45, 72 and 50. So, those values are very small values, I understand, but a window for one window, for maybe there are 2 such windows, this is a very small window. So, 2 such windows may improve this value, we have to see. So, that one has to be calculated. The case 2 and case 1 are devised from the base case. So, case 1 you see we have increased the width 2 meter to 3 meter and there is a considerable change I have seen in the DF. Of course, there is a window area is also going to be changed, but you see the case 2 window area is decreases 0.45 to 0.4. This is very important. So, this is a decrease in the window area, but your this is remains same, the illumination or the daylight factor at A, but the illumination or daylight factor at B, the higher depth is increased, even though it is a 5 lux does not matter, but it is increased. So, theoretically say it is better to increase the depth of the window instead of increasing the width, it will going to illuminate the higher deeper part also of the room. So, that is all for this particular lecture, but yes, this is another particular graph. I think no, there is 2-3 things also we have to discuss over here. One is this is the distance, when if the distance increases from the window, the DF is going to decrease, that we understand from our other calculations also, and there are some other ratios like uniformity ratio and all. So, what is the DF minimum and what is the DF mean of all the points of some of the strategic locations of the room or so, then we can find out the ratio between the DF minimum and the DF maximum, DF minimum and the DF min. So, that will give me the some uniformity ratio. So, we can also there we can use some kind of a thumb rule. This is another thumb rule, the gross area if you want to find out from the DF. So, you can use this equation, the area of gross area of the glazing of or in the window. So, DF, how much DF you want is the 2% or whatever, AF is the area of the floor 0.2 and the TG is the visible light transmissions. So, suppose I have a the room size of 4 meter by 6 meter and VLT is your 0.45, daylight factor I want 2. So, how much area of the window I can give? So, the area window glazings comes out to be by this formula. It is a thumb rule, it is a thumb rule formula 5.33 because 24 is my the area of the floor and this is 0.45 is my that the VLT and 0.2 is my daylight factor I want. I mean 0.2 is the this particular value, this constant value, and 0.02 is the daylight factor. This is the daylight factor. So, I can actually go for 5.3 meter square or so. So, that ends this particular lecture. So, we discussed about the mostly on daylight factor in this lecture, and we see that the impact of the window size, window mostly on the window width and the change of window the depth, how it going to decide the daylight factor. Thank you very much.